Good morning. I'm very glad to introduce Keith Frikken. He's a PhD student from the CERIAS department. He's also affiliated with CERIAS. He does research on a number of different topics concerning information security, and he's also doing work on database systems. We are really proud to have him as a CERIAS student. So I'll give the floor to Keith.
I'd like to welcome everyone to my talk on hidden access control policies with hidden credentials. If at any time you'd like to ask a question, just let me know. Feel free to interrupt me at any time. The motivation for this work is that traditional access control models where you have someone requesting an object and where the object is, the decision to give the access to the object is usually given by the identity of the requester. The problem with this, if you have an environment like the internet, is that perhaps the requester and the resource owner are in different security domains, so having an identity doesn't make a lot of sense. Well, one of the typical ways that this is handled is instead of basing it on the identity of the requester, you can base it on the attributes of the requester. Of course, for such a system to work, you need some entity that will say, well, this person who has these attributes, I verify that they have these attributes. If you don't have such an entity, there's no real trust between the system because one person can just lie about what attributes they have. The typical way this is done is through some form of digital credential. And they can have many different types of digital credentials. You can have one for citizenship, perhaps age. Fairly common for many services, you need to be above a certain age threshold. Some physical condition, your employment status, a credit status, a membership in a group, or even a security clearance. In the last case, the security clearance becomes particularly interesting because many times, having something being at a certain, sensitive level, that itself is a sensitive information. Now, you could probably tell that, well, there's lots of things you could have attributes for, and if you had credentials for everything, these would be very sensitive. You wouldn't want to go around just telling everybody, here are all my attributes that I have. One, they could probably link back to your true identity, and then they know everything about you. But also, there are situations where the access policies are sensitive. Typically, in top secret type instances, you'll have many cases where the fact that this document is top secret in a certain project is sensitive, and you don't want to tell everybody that asks for that document that this document has that statement. But even in cases where things are not sensitive, immediately sensitive, there are advantages to treating them this way. First, there's better individual privacy. You wouldn't want to just go out, this is fairly obvious. You don't want to go out and tell everybody all of your attributes, even if they don't know who you are. Because every time you tell them some of your attributes, they learn more about you. But on the access policy side, if the access policy for a particular object is publicly known, then you know exactly what you need to get access to that object. So you can try to game the system. And if there are usually economic systems where you know everything about it and that you can guess things, it usually makes them less effective. However, a common criticism of this is, well, if I trust you enough to give you an object or for us to even talk, I trust you enough to kind of know some information about me. So we trust each other. So this, common criticism, well, if there's mutual trust, this doesn't happen. But there's better security even if mutual trust exists. If the two people negotiating trust each other, but Alice trusts Bob to know her credentials, that doesn't mean she doesn't have control over Bob's system. Bob's system could have spyware or many other things on it where someone else could get Alice's information by compromising Bob's system. And similarly, in the other way around. So it's just better security as a whole if you don't reveal these credentials and access policies. Also, if Bob comes along and creates some very novel business strategy that allows him to gain some competitive advantage, he doesn't want to go broadcast to everyone, well, this is what I'm doing with my access policies to give me some advantage. And thus, he'll have fewer immediate imitators, so he'll be able to gain some advantage. Just as kind of an overview here, the model of the computations, we have Alice, who we'll call the client for this negotiation, and she requests some message from Bob, we'll call it M. Bob has this message, and he has some policy for the message, or conceivably several policies for the message. And our goal is to create some type of protocol where Alice can input her credentials and that Bob can input this message in the policy, and that Alice will get the message if her credential satisfies the policy. Now, this really can't use a third party. If you had a trusted third party between Alice and Bob, the solution is fairly simple. Bob sends the message and the policy to the trusted third party. Alice sends her credentials to it. And then the third party makes a decision and sends Alice the message if possible. And the difficulty with this is it's hard to find a trusted third party. That being said, there is a third party element to this protocol. There is someone that is certifying Alice's credentials. And this party doesn't work for this entity because Bob doesn't necessarily trust that entity with his policies. He trusts that entity to a degree to verify Alice's information, but that doesn't mean he trusts that entity to know his policies. Also, there's a difference between that entity knowing all of Alice's attributes versus knowing all of Alice's attributes and what she's asking for. So having that credential authority make the access decisions and be this trusted third party isn't desirable for either Alice or Bob. On top of that, if you were to use the trusted third party in that regard, it would become a bottleneck in the system. However, when you have a trusted third party, it is a fairly nice solution. You have a situation where, Alice and Bob does not learn anything about Alice's credentials. So our goal would be to have a system without a trusted third party where Bob does not learn anything about Alice's credentials. Bob does not learn whether Alice gets access or not. And this is nice because if Bob knew where Alice got access or not, he could change his policy every time Alice asked for something and glean information about Alice's attributes. Alice does not learn Bob's policy structures nor which credentials caused her to gain access. In our solution, we try to achieve a couple more things here. Alice cannot probe offline. She can't request the message once and then try different sets of credentials with just that one request to try to figure out if she has. You have a question?
Okay, so if Alice learns neither Bob's policy structure, when the basis of Alice wants to receive document X, she knows she can receive document X because, well, I have a security clearance or I'm of an age of X, so I should be able to get to it and then make the request that way.
Well, there are cases where that would be true. There are other cases where Alice thinks she might have the message, might have authority to get to the message, and perhaps she doesn't. And so she could request the message, and then if she doesn't get the message, she learns, well, I don't have access to that document. Perhaps she learned about the document through other documents that link to it, or something like this. Also, the policy needs not be monotonic. So you could have something like the absence of an attribute. Now, our goal is to try to achieve all these properties without a trusted third party. And a trusted third party, you can achieve all of these fairly easily. Now, the solution we'll talk about later gets close to achieving all these. It can't achieve all of these. Bob does learn like an upper bound on the number of attributes Alice has. It's kind of unavoidable without a trusted third party. Also, Alice learns a little bit of information about Bob's policy, but she doesn't learn everything about Bob's policy. There are some practical considerations to this, though. The first is that a non-monotonic policy might not make sense. You can't force Alice to use all of her credentials. She can choose which ones she uses. So an example would be, suppose Bob wanted to have, Alice does not have a credential saying she has a bad driving record. Well, if Alice has a credential saying, I have a bad driving record, Alice is not going to use that in a situation where, if I'm applying for insurance or something like that, why am I going to use my credential that I have a bad driving record? So in this case, you can't force Alice to use her credentials. And so she can use any subset. So if you have a non-monotonic policy, Alice just looks at her credentials beforehand. Do I think this will help or hurt me when getting access to this document? Now, if you use a monotonic policy where you don't have the absence of a credential, then her best bet to getting access to a document is to use all of her credentials. It makes it so that it's most likely. However, if you have this non-monoticity, this isn't the case. But there's more practical problems with this. A lot of times when you're asking for an absence of a credential, that's a fairly special case. Most people don't have that credential. And so you can try to reverse it. So in the case of the bad driving record, you could have a credential for a good driving record. But if you did this for all the possible things where you could have a not of something negative, most people would have to get a very large number of credentials, which make the system not usable. But there's another problem. So consider a credential for this person is a millionaire. It's fairly easy to prove to someone you are a millionaire because you can go open all your bank accounts, you can open up all your, get all your credit reports out so they know how much debt you have, and you can show, well, I have a net worth over $1 million. But proving to someone that you're not a millionaire is much more difficult. How do I know that you don't have $1 million stashed away somewhere in your basement somewhere? And it's much harder to certify something like you are not a millionaire than it is something to have you are a millionaire. So having the absence of a credential doesn't work in many cases. Also, even if you have a trusted third party, Alice can carry out an online probing attack. She can ask Bob for the same message many times. And each time she can try a different set of her credentials and therefore glean information about Bob's policy. This is unavoidable in our model. However, it's worth noting that Bob really can't do this because he doesn't know if Alice gets access or not. This being said, there are cases where Bob can infer information about Alice getting access or not. Suppose that a message M1 has a hyperlink to message M2. And shortly after asking for M1, Alice asks for M2. Bob doesn't know that Alice got access to M1, but he knows with some degree of certainty that she did. So Bob might be able to do some form of probing with these types of techniques. We don't really consider this a big problem, though, because Bob knows when Alice is doing this to a degree. Because if Alice is asked many times for the same message, Bob knows this. So he can just implement a simple policy. He can only ask the message person. Yes?
You said if Alice was granted access or rejected access, she wouldn't know the reasons why, which
right.
Wouldn't that, in a realistic situation, be more of a hindrance than a good thing? I mean,
it depends on what you're doing, right? I mean, yes, you could have... If someone had a bad policy, you have to be of a certain ethnicity to get access to this. That would obviously be something that's bad. However, in like a government situation where you have top secret clearances,
right,
that is a very desirable thing that you don't know why you didn't get access.
Well, wouldn't you if she's working for, say, the CIA and she has the wrong security clearance, I mean, she doesn't know if it's because of her security clearance, department, gender, or whatever, and
well, it does depend on your situation, right? I mean, yes, you could, if it's an internal CIA server, then, it's probably not the case that they're going to deny something because of gender, right? It's more that they're going to deny something because of security clearance. And a lot of times, like the different departments in a top secret project have confidential names. So they can't just go around telling everybody the access policies.
Right.
Also, if you take an example like the TSA, they have certain criterion they look at, but they don't want people to know those criterion, right? Because if they told everybody those criterion, well, it makes it that much easier to game the system, gain access to the system. So there are cases where you don't want to reveal that information. There's a lot of work in trust negotiation that's fairly similar. A lot of times, some of the work tries to minimize the disclosure of credentials or policies. However, they don't quite achieve what we've achieved before. They usually have something to the degree of, if you gain access, you found out why you gain access, which is something that we're trying to prevent. This being said, it's not that this work completely, this is a superset. The work that I'm presenting is a superset of this work that is better in every way, because while ours has a higher degree of privacy than a lot of this, it also requires more computation and is more inefficient. So it's kind of a proof of concept that you can do all of these things rather than an efficient system that's useful. There's also some related work in the area of secure multi-party computation. Secure function evaluation, particularly, it allows, if Alice and Bob have private inputs A and B, it allows them to compute some function that's an aggregate function on those inputs without revealing anything other than the input and output alone, which clearly has a relation to what we're doing because we want to be able to evaluate a policy without revealing anything other than what can be inferred from the input and output alone. The difficulty there is that the function in secure function evaluation is usually a public function that everybody knows. And so it doesn't quite work because in our case the function's hidden. One person knows the function, the other person has the inputs. There has been some work in a secure private function evaluation, but this was really more about special cases. And the model was that one person has a large data set and another person has a particular function. And the person with the function likes to evaluate the function on a subset of the data set. And so it's not quite the same model that we're at, but it is related. Also, a special case, a particular secure protocol that has an implication is a secure private intersection. This being said, there are some differences between the related work and this work. First thing is that in typical secure function evaluation, one of the things that's always said is that, well, Alice can lie about her input, Bob can lie about his input, which makes it not immediately usable in this case, because if Alice's input is her attributes, she can just lie about her attributes, which makes Bob have no trust in the system. But instead of this being the case, it's really a third-party verification of the attributes. This is complicated by the fact that this verification is done by a certificate authority who does not need to be online when this is happening. If the certificate authority was online when this is happening, you could expand to a three-party protocol or something to this degree. But if you had the certificate authority being an active part of this, it would become a bottleneck in the system. What makes this different from a lot of the work in trust negotiation and hidden credentials is that the goal is to reveal nothing. You're not supposed to reveal Alice's credentials. You're not supposed to reveal the policy. And you're not even supposed to reveal the outcome to Bob. So there's a high degree of privacy requirements. So at this point, we've been over kind of what the goal of the system is. There's a few building blocks that are used by the system. One is scrambled circuit evaluation. And this was introduced by Yao in 1986. And essentially, it says if you have a two-array circuit for evaluating some function f, and it has m gates and m input wires, then you can evaluate this with order m communication and order m evaluations of some pseudo-random function. An example of a pseudo-random function would be something like AES, which is fairly efficient. Also has order n 1 out of 2 oblivious transfers. Oblivious transfer tends to be a fairly expensive operation. Usually requires some form of public key crypto, so something on the order of a modular exponentiation. But it also only requires a constant number of rounds. In order to explain things later, there's the way this protocol basically works is there's a circuit generator who creates some scrambled circuit of some form. He sends this over to some evaluator, and the evaluator, while each doesn't know what he's evaluating, what he's evaluating, but he does know at the end of the day what the circuit computed, but he doesn't know what the intermediate values are. Also, there's a particular secure protocol, set intersection, that was introduced in 2004. And in this, we use a kind of a special case of this. This is a one instance of being able to do this. And basically, Alice has some set of values, and Bob has some value xb. And if xb is in the set of values, I flipped the XA should be XB and SB should be SA in the later part of the slide. And if XB is an SA, then Alice will learn the value RB. Otherwise, she learns some random value that's indistinguishable from RB. So at the end of the protocol, Alice doesn't know if Bob's value is in her set, but she has one particular value that is something if it is in the set. And this requires communication proportional to the size of the set and a similar number of modular exponentiations, yes.
And does that use a trusted third party?
No. It's a two-party protocol. It can be secure in a malicious model and all these things. One more building block is identity-based encryption. This was proposed by Shamir in 1984. And basically, in this case, it was a request. We'd like a crypto system with the following properties. And there were many systems that attempted to achieve this that either fell short or were subsequently broken. There's been a recent scheme in 2001 that actually achieves this in many ways. But the goal of the identity-based encryption system was to implement a public key infrastructure for an email system. So you'd have some key granting authority that would kind of play the part of the public key infrastructure, I guess. And there were basically four parts to this. One was a setup algorithm, and this key generating authority would run this algorithm and generate some public parameters that everybody would know. It would also generate some private parameters like a master key. And there was an extract algorithm that if you had the master key for any string, you could create a private key corresponding to that string. And also, but if you had the public parameters, you could generate a public key for any string. So the encryption algorithm would take any string as its input, would be able to create a public key towards that, and then encrypt it with that public key. And if you had the private key for that public string, you'd be able to run a decryption algorithm to decrypt messages. This is fairly nice for an email system because if I have someone's email address, well, I can get the public key because I have their email address, so I can create the public key for that. And the key generating authority won't give them the private key unless they have, if they're the person corresponding to that email address. So I know I kind of have a public key infrastructure, and I don't really have to, talk to the key generating authority other than once for everybody. There was some work in 2003 on hidden credentials, which was kind of a starting point for this work. And the credentials are generated by some certificate authority, and it uses this identity-based encryption. So this is a quick example. Suppose the certificate authority wants to issue Alice a student credential. Alice could be some form of pseudonym, or it could be Alice's email address or something like that. Now, he could use the identity-based encryption with the ID of Alice concatenated with student. And if he agrees that Alice is a student, then he can give her the private key corresponding to this ID. And if she's not a student, he wouldn't give her this. So this this credential authority kind of plays the part now of verifying whether or not Alice should gain access. Just as a quick example, suppose Bob wants to give Alice a message M, where the message M should only be read by someone that's a student. So Alice asks Bob, I'd like message M, and Bob would then compute the public key for the ID Alice concatenated with student. He would send Alice this value. Now, if Alice has a student credential, she'll be able to go to the certificate authority and say, I would like, the private key, or she probably already has that if she has that attribute. So then she can decrypt the message. Now, note that Bob does not learn whether or not Alice is a student, but Alice only gets the message if she is a student. This doesn't, even in this simple case, this doesn't solve what we were proposed earlier, because note that Alice does learn Bob's policy if she gains access. Before we get into the protocols, a quick note on how we're going to define the policy. And we're going to define this simply by some Boolean function p over some values x1 through xn, where the x values are binary values. And the xi corresponds to the absence or presence of an attribute I. Now, if Alice's set of credentials will satisfy the policy, if we let these x values, xi will be 1 if there's a credential that corresponds to attribute I. So if the p function of these x values is 1, then Alice should gain message. It satisfies the policy, otherwise she doesn't. As a quick example here, suppose Alice is a senior citizen and has a low income. Furthermore, suppose the policy is you need a disability or be a senior citizen and have a low income. Well, Alice satisfies this policy because she is a senior citizen, which would correspond to x2 here, which is 1, and she has a low income, which corresponds to x3. Therefore, the policy function values are true. So there are two parts to being able to do our desired goal. The first is that we kind of need the credentials and the attributes to be hidden in some regard. Alice has a certain set of credentials, Bob has a certain set of attributes in his policy. We kind of need it so that Alice and Bob are speaking some language that the knowledge of which attributes Alice has is both verified by a certificate authority, but also is done in a way that neither Alice or Bob know which credentials or attributes the other side is using. And the way we're going to choose to represent this, the goal of this phase is that Bob will have two random values that he's generated, RI0 and RI1, for each attribute. And Alice will know one of these values, and only one of these values. She won't know which value she has, but she'll have exactly one of them. And furthermore, if her value ki is RI1, that means that she has a credential for the attribute. If ki is RI0, that means she doesn't have, or she didn't use a credential for that attribute. Now, note that Alice doesn't need to necessarily know which value she has. The RIs are chosen from a fairly large domain, so she can't just guess a bunch of RI values to guess the other one. Once you have things in this format, the goal is to take this and then basically evaluate the policy function P. The hiding phase is actually, of the two phases, is the more difficult of the two phases. Suppose Alice has a certain set of credentials C1 through CM, And that Bob has these n pairs of random values that he's generated, Ri0 and Ri1, each corresponding to some particular attribute. And the goal is, though, Alice will get one element from each of these pairs, and it will be Ri1 if she has some credential C sub j where the attribute for C sub j is attribute I. The first step is Bob's going to generate n pairs of another, for each attribute he'll generate another pair of random values, ki0 and ki1. And the goal will be to kind of slowly work towards the desired output by having the value split in some other fashion. So to begin with, Bob will send Alice, he'll encrypt for each attribute, he'll encrypt ki0 with Alice concatenated with the ith attribute. Now Alice, if she has attribute I, she'll be able to decrypt this and get ki0. But suppose she doesn't have attribute I. She doesn't know what attribute I is, so she'll basically try all of her credentials. She'll try the private keys for all of her credentials. When there's not a match, she's decrypting something with the wrong key. When you decrypt something with the wrong key, you get something that looks random, that looks like garbage. But this is no different looking than ki0 because ki0 was generated from the beginning to look like random looking garbage. So she doesn't know, when she decrypts all of this, she doesn't know if she has the particular attribute or not. But she can create, for each attribute, a set of size m, which possibly would contain the value ki0. It will contain ki0 if she has it. It won't contain ki0 with all but a negligible probability if she does not have the credential. Now this is where the fit intersection protocol comes into play because Alice and Bob engage in the set intersection protocol with ki0 being Bob's input and bi being Alice's input. Now, at the end of the protocol, though, Bob would like to reveal out to Alice ki1 if ki0 is in bi, and otherwise reveal some random looking value. This doesn't reveal anything to Alice either because ki1, again, is a random looking value, and so it's indistinguishable from a random looking value from something not being in the set. At this point, though, Alice will have the credential if her value that she got in this previous step will match ki1. So now we're basically in equality. If they match, Alice has the attribute. If they don't match, she doesn't have the attribute. Note that Alice does not know if she has the attribute or not. That's been questioned. And Bob doesn't know if she has the attribute. And there are, using a scrambled circuit evaluation, it's a fairly simple circuit to implement where Bob's input's ki1, Alice's input is the value. If they're equal, Alice will learn Ri1, and if they're not equal, she'll learn Ri0. So just kind of an overview here. We started out with the information completely split between Alice and Bob, and we've kind of did 3 steps here to transform it into this format where Alice has one value if she has the credential, and the other value if she doesn't have the credential. Are there any questions on this phase? It's kind of the...
Yeah. Sorry. So these are does Bob send these to Alice?
No, he creates them. He creates them on his own system.
So I guess I'm a little confused when you say she gets R1.
She learns the in scrambled circuit evaluation. You get to choose 2 encodings for each wire.
And this circuit evaluator is sitting at her end, or
Bob generates some circuit for his value ki1. But the output wire of the circuit, if there are equal, is Ri1, which she would learn as Ri1, and otherwise it's Ri0.
What you're saying is that Bob can not know which one of those she got.
Right. So Bob knows what things mean. Alice doesn't know Alice knows what the actual values are, but she doesn't know what things mean. Bob doesn't know what the things are, but he knows what everything means. So that in that way, the information is split between Alice and Bob where no one of them knows any useful information. The second phase, policy evaluation. So after this step, Alice has some value ki, which is either Ri0 or Ri1. And we'd like to evaluate this function p of x1 through xn. Note that xi is ki equaling Ri1. And so we'd like to evaluate this. Now, there's a couple ways one could do this. It's kind of a simplified version. This version here reveals a little bit of information to Alice about Bob's policy. After this, I'll talk about how you can hide that even further. But Bob sends to Alice some encryption with any system, probably something like AES. He encrypts M with the value K. And so knowing M is equivalent to knowing K. But one of the things with scrambled circuit evaluation is that each wire has two encodings. Well, it's convenient that the encodings are already split between Alice and Bob. So we don't need to do an oblivious transfer or anything at this point in time. We can just build the scrambled circuit for the policy. Of course, this does reveal to Alice that Bob's policy can be evaluated with a circuit with the following topology. However, a lot of useful circuits can be built that look the same. So Bob could create kind of a uniform circuit that could evaluate many different types of policies. And Bob will send Alice this scrambled circuit, and Alice at this point can evaluate this circuit. And the output wire, if the policy is satisfied, will be this key value K that Bob has generated. Otherwise, it'll be some garbage value. And when Alice has this K value, she can easily look at this, and if it's the one encoding, she'll get M, otherwise she won't. The only real problem with this is that the scrambled circuit does reveal a topology of this. If Bob's in a situation where even the topology of a circuit is too much information, there is a fairly simple exponential communication system. You can create a single circuit that only consists of one gate with n inputs, and that you can evaluate it with basically order 2 to the n communication. At this point, I'd like to open up for questions. Are there any questions? Yes.
So the correctness, so one of the correctness criterion is that, for example, Alice doesn't learn the access policy of Bob, right?
Right, or the policy is as hidden from Alice as possible.
But like somebody else, gave the example before, she may already know it.
Right.
Just as an example.
Yes.
So then the correctness criterion should be tempered based on that, am I right? It should be something like that perfect secrecy thing where I don't learn anything more or something. Do you see what I'm saying?
Right.
If I already know this, and this, then that's all I know after.
Right.
Basically, I'm wondering if you actually have these correctness criteria stated formally and with the proofs, or is it just...
We have semi-formal proofs that this works. Essentially, we show that if you have perfect implementations of the two phases, that the resulting protocol would be secure. Therefore, if you have a implementation of each of them, you can, using composition theorems, can compose them together. Now, with regards to if they have previous information, basically the method of proof that we use is that if you have a trusted third-party implementation of this, that you can simulate everything that you see in the protocol. So therefore, the protocol doesn't leak anything other than what engaging in the protocol leaks inherently. Because even in the trusted third-party case, some information is leaked, right? Because Alice knows with this set of credentials, I know I can get access to this policy or not.
So you're saying it's no worse than if you use a trusted third party?
It's no worse than if you use a trusted third party, which is, a lot of times in secure protocols, is the way that you prove something is secure. Yes?
I have one more general question, which is the following. So, suppose you have done the negotiation which is successful.
Yeah.
At the end, Alice will access the resource.
Right.
How do we prevent Bob from observing?
Well, the way that we do this in the blended policy evaluation here was that he sends to her at the beginning EK of M. So, of course, if she doesn't learn K, this doesn't tell her anything, so she doesn't get the message. But the only way that she'd ever get K is if she satisfies the policy. So she kind of gets, at that point in time, Bob won't know because she won't make another request for M to Bob.
But, no, I'm saying, somehow this, you have the assumption that the only thing that she will get is a message M.
Right.
Okay. But what I'm asking is that then she will have to access the real resource, which could be a file or...
Oh, okay. Well, I neglected to mention, the assumption that we're kind of using is that the resource that you're asking is something like a file. It's a one-time resource. It's not a service-based thing. If it's a service-based thing, there's other questions. This could be used to have it so that you can make the access decision, but then there's another question. If you have a service, how do you give that service without Bob knowing if he's giving that service?
So the question was exactly how you combine, or how can you use your protocol, maybe extending to that environment as well.
Okay. That's one of the things that's actually kind of open that we've been kind of working on. We don't have a solution for that at this point. Yes?
So I think it was the Holt, Bradshaw, Siemens protocol.
Yes.
Where you said that Alice could learn Bob's access policy because he just uses the identity-based encryption.
Right. That was the original hidden credentials. There's been another hidden credentials paper which kind of does a little bit more complex policies. It has some more types of hiding.
So I was just going to ask, well, what if Bob just asks for a bunch of other garbage? Oh, do you have a driver's license? Are you over 21? All this stuff. But he's actually only going to use...
Right. That is actually supported by our system. But one of the differences between like the hidden credentials work and this work was that Alice learns when she satisfies something in Bob's policy. Even if it doesn't get used, she learns that she satisfies something in Bob's policy. Whereas she doesn't learn that in this case. Thank you.
Now, just trying to get into a completely different part, which is what you were saying about negative credentials.
Yes.
I was thinking about it, and assuming that the issuer of the negative credential is also someone who issues a positive credential that you would otherwise need, you could probably use some sort of integrity measures, digital certificates, to ensure that negative credential is being provided if it exists.
Yes, that is a possibility if the credential authority does more than what it does in this system. Right? The credential authority has to kind of be an enforcer in that case and say, well, you have to use all the things that I gave you, not just one of them.
But I think you can, that should be, there's more to it to get into that, but there are integrity approaches to ensure that if they're providing anything from that credential authority, they're providing everything.
Right. Not sure.
Bertino's done some work.
Yeah, that would be an interesting twist in the system. I haven't considered doing that yet.
That might help with you kind of built something to allow these negative or non-monotonic. Yes. It would be nice to it would give you a way to make that more.
Well, I guess the other interesting thing is that while the system supports non-monotonic, if everybody used non-monotonic, people would think about things, but if people were just mostly using monotonic policies, you could probably throw a non-monotonic policy in every once in a while without anybody noticing. But still, if I'm not going to use, right, so it's...
Yeah, can I also use that? Actually, if you can integrate everything together, you use traditional digital driver, use digital certificate. But in the hidden credentials, usually each credential only have one attribute, so that you cannot combine things together.
But if you come from the same credential authority, that credential authority could say...
Yeah, if you have a digital driver license...
You could still separate it, but there could be it's not easy. There's a lot involved. But.
And another difficulty with it is that you might have a lot of different attributes, and of course, the complexity of this is ordered the number of attributes that you have in the policy and the number of credentials you're using. So if I have a large number of credentials with this one person, I have to use them all now, and that might make the system not usable. Whereas in another situation, I can say, well, for what I'm applying for, these are the things that are going to help me. And so I can make it a more efficient protocol. It'd be another problem with doing the integrity things. It would make it possibly unusable in some cases.
I think we have some time. Can you maybe outline some future work that you
outline some future work in this area? Okay. In this particular area, well, one of the things that we're looking at, like I mentioned, is things for services and other things like this. But in the trust negotiation area, there's another thing that's a consideration that we don't consider, and that is that I will only use my credential if you have authority to see the credential. And for things like the message inference problem, where if I have message M1 and then ask for M2, then I could probably infer that you got access to M1. Well, if Bob is semi-malicious, he could have the policy for M1B. You have to have top secret clearance for something. And perhaps I can't show you I have top secret clearance unless you have top secret clearance. But now you have this inference thing where Bob might be able to learn that, so I can't use my top secret clearance credential unless I know Bob has a top secret clearance credential. And it's not clear how do we have this so that you could have both people enter a set of credentials, and each credential kind of has their own policy now. And I will only use this credential if I have a policy, if you've satisfied my policy for that credential. How do we kind of merge all these things together in a way that I'm only using the credentials you have authorization to see, you're only using credentials that I have authorization to see, but based on those credentials, do I get access to the document? I'm also doing some other work in other types of secure protocols. I've done some things with contract negotiation, which is a different type of negotiation entirely than this. This is kind of a trust-based negotiation. In that, Alice has a set of requirements for a contract, and Bob has a set of requirements for the same contract. And these constraints it might be the case that these constraints don't satisfy each other and that there's no way there's a valid contract that satisfies both persons' constraints. But you'd like to know those securely without telling you, well, here are all my constraints about my business practices and here are all my constraints. Now let's match them up. So finding a secure way to match constraints is the first part, but then suppose that things match. Well, that doesn't do us any good because now we have to figure out a valid contract that we both agree to. So the second part is how do you generate a contract that's fair and fairness is something to the degree of I can't control the outcome. Of all the possible valid contracts, they're randomly chosen between them. Of course, there might be situations where you have a win-win situation where Alice and Bob both prefer one contract over another contract, and we also have a filtering type process that would allow that only efficient, fair contracts are chosen. Some other work, I've done some things with biometric comparisons. Basically, how do you implement a PIN system with a biometric smart card? A normal PIN system is fairly easy to have a secure check because equality checks are much easier than approximate checks. So how do you develop protocols that will tell the bank essentially, yes, this person is the person that they're saying they are, without revealing the fingerprint to the bank? Other work, I've done some work with privacy-preserving electronic surveillance, where you have some government entity that wants to monitor a subset of the population because they have perhaps they have some type of warrant, or they have some credible suspicion that this person is doing something. Now, this person has a right to privacy. It's not right to go out and publish, we're looking at all these people, because this person has some right to privacy, because they have not been convicted for anything. But the second thing is that if I go out and tell everybody, well, these are the people I'm looking at, it makes the surveillance system less effective, because if I have a friend that gets this list, of course, I'm going to disappear and not use all the identities that they're looking for. But another problem is that you can't just send to this government agency every transaction that's done by everyone, because they have no right to monitor someone that's not at least suspected for anything. So the question becomes, how do you monitor a subset of the population without looking at all of the population? Those are just some of the things that I'm working on related to this area.
Thank you.